Recording is rolling. It's Monday, February 2nd. I'm going to do lesson 8.5 with you guys today using exponential and logarithmic functions. Tomorrow I'll do 8.6 with you guys, which is about interest rates, simple, compounded, continuously compounded. Okay, so, and that will wrap up module 8. Alright, so how do you guys keep notes today and tomorrow? So you guys have some paper. You guys write your name on your paper. Everybody writes your name. Nice. All right, so everybody's got the name on the paper. Right, name on the paper. Okay. So we'll do again, we're just gonna focus on 8.5 today. Just take some notes. You guys turn in those notes, and you guys get points today. Over the weekend, I opened up the next Alex assignment with so 8.5 and 8.6. Again, a single assignment on Alex. Have you guys keep notes about the first half of class today, and then second half of class, you guys can open up this assignment, start looking at that. Yeah. So tomorrow 8.6. Wednesday, I plan to put together for you guys for review. Thursday, I think would be a good Alex day, and then Friday quiz. Right, so quiz Friday on module 8. Module 8. Right? Okay. Any questions about the agenda? What we're doing? Right. Good. All right. Going on then. So these last two lessons, which also over the weekend I recorded longer versions of lots of examples of these. I don't think there's anything extraordinarily new. It's just applications of things that you guys have been learning for the past couple of weeks. Okay. You guys remember this page of log rules? Okay. Actually, this is good review right here. Okay. So coming back from the weekend especially, right? And so this is what we've been working with the last couple of weeks and what you guys have to know for the quiz this Friday. Okay. Oh, the quiz this Friday, by the way, I did print this page of rules. Okay. So I want you guys to be able to apply these. Right? But here's what you've been seeing over and over. So if you have an exponent form like x to the y z, you can rearrange that, make it log base x of z is equal to y. Okay? You guys know these are inverses of each other on a graph. We got this product property. Log of a times b is log a plus log b. Quotient property, log a over b is log a minus log b. Okay? Log a to the power b, now we got this power property. You can pull the b down, make it b times log a. Okay? If you have some weird base, because remember your calculator knows base 10 and base e. That's what log and ln are. Base 10, base e. What if you had like log base 7 or something weird? Right? You can switch base by doing log of a over log b, which or if you like natural log a over natural log b. Okay? And then a couple of bonus facts. Okay. All right, so got some log rules. What could you realistically apply these to? Okay? In the longer video, I went through, of course, all the book examples. So continuous exponential growth. This one here, there's a table of values for like population of Florida. Okay? I went to Desmos and put in the table of values and fitted a curve of best fit, right, with an exponential growth curve. Okay? Which we've done a few times in class already, but if you wanted to see an example of that again, you guys get that. Continuous exponential decay. I've been showing you guys this poster from time to time. Okay? So any atom that's radioactive, for example, carbon-14, that's a certain isotope of carbon, okay, has a certain half-life, okay? Which means that when one of those half-life periods have passed, now it's decayed to half of its original value. So if you start off with some original value, in the case of carbon-14, it works out to 5,730 years. Now you're down to half of what you started with. Roll ahead another 5,700 some years. Now you got half of that. Now you're down to a quarter. Roll another 5,700 years. Now you're down to an eighth. And so keep going on, right? Okay. And so there's this fun application where you can say if you find some artifact or some sample and it has like an eighth of whatever radioactive isotope that it should have started with, you can say, oh, well, I know 3 half-lives has passed, and that's how you can date the artifact. Right, so there's this example here with coral. They use thorium-230. Right, so that's another radioactive isotope. Here's radiocarbon dating. Okay, so like traditional archaeology that you can go back thousands of years with. Okay. I'm going to jump in and do some other examples for you guys that are not in the longer video. Right, so you guys have more examples. Let's do number 2 right out of the book here. Number 2. Jason wants to buy a new HD television. But he thinks that if he waits, the quality of HD televisions will improve. The television he wants to buy costs $2,500 now, and based on pricing trends, he thinks that the price will increase by 4% each year. Write an exponential growth equation to write the price of a new HD television T years from now. Use the equation to predict when the price will be $3,000. And then there's a part C, but let's be part A versus right. So one thing at a time here. So number two, they just told us this. The current price, I'll call it P naught, is $2,500. Right. So if he doesn't wait any time at all, he just rushes straight to the store. That's the price. Okay. He thinks the growth rate, I'll call it R, is going to be 4% per year. Okay. Because when you go plug in numbers in the calculator, 4% growth, you don't want to type the number 4. You want to type the number what?
0.04.
Yeah, so 0.04, right, and oftentimes I'll add it to 1 to represent a growth rate, 1.04. Okay, okay, so 4% is the same thing as 0.04. You know that. Is that going to be helpful? Okay, and exponential growth rate, oftentimes your book wants to use the eventual price, let's say price is a function of time and years that have passed, is equal to the original price times. You guys remember continuous compounding? It was like e to the RT or e to the KT, something like that. Okay, so let's fit it into this model. This is probably what your book is looking for. Okay. And we know some of these values. So I know that we're starting off the original price is $2,500. Right. We'll use continuous growth rate here. So can't we have the E? Okay. We have a growth rate of 0.04. Right. Now, if it was like, actually, this is kind of a matter of interpretation. No. Let's see. Annual interest compound.
It's growing, right? So
Yeah.
1 point or no?
Huh?
Maybe 1.04 or no?
Well, okay. Thing is, here, let me show you guys this. Okay. If I,
That's on module 8.
Friday. Yeah.
This Friday?
Yeah, this Friday. Yeah, I'll do, okay. So we're covering last couple lessons. Here, show you guys. We're covering last couple lessons today and tomorrow. Okay. Wednesday I'll do review with you guys, and then quiz Friday. Okay. All right. So if I do e to the power of 0.04, right, subtract 1 out of that, you guys see it's actually like 4.08% or something like that. Right. So it gets kind of fuzzy as to how you construct this exactly. Okay. So there are different interpretations where you can get slightly different answers, but I'm just gonna run with this interpretation. Okay. I'll put T up here for number of years that have passed and like P of T here. Right, smooth that. Okay. And we're looking for exponential growth equation. Right. So this could be the answer. Okay. Well, let me actually go with the other interpretation. Let me put or. Right. And here's the other interpretation you could have. You could have starts off with $2,500 and then times 1 plus R or 1.04 to the power of T. Right. Now, guys, these are slightly different curves. They are not exactly the same thing. But how do you interpret that 4%? Is it continuously compounded or is it like annual? Right. So if they didn't specify, then okay, well, be one or the other.
Or you have questions like this on the test that we
if I put a question like this on the quiz, I would tell you whether I wanted it to be continuous or annual. Yeah, right. I mean, I wouldn't leave it ambiguous. Right.
Will this one be annual though? Because you said 4% every year.
Yeah, we could go with that. Let's do that then. Right. Right. So yeah, if you want to do it like that, we could do that. Right. So when will the television cost $3,000? Let's try it with each interpretation and see how much time it takes. Because it should be a very, very similar answer, but maybe slightly different. Okay. So here's continuous. Here's annual. Right. Maybe that's what I should do is like split the paper and run each interpretation. Okay, and see how it's turned out. Right. So we'll try a continuous model. We'll try an annual model. Right, we'll see how do the times compare even? Yeah. Right. And so we're aiming for $3,000, starting at $2,500, and then e to the 0.04 t. Whoops, t 0.04 t. I suppose that one. Okay. Or I could go $3,000 equal to $2,500, and then 1.04 to the power t. Like that. Okay. Okay, let me rewrite this. That's kind of bunched up there. 0.04 t. There you go. Okay, that's the power there. Okay. Yeah. All right, now, what's the next algebra step? Either method. Yeah, divide down this 2,500. 2,500, divide down. Okay, same thing over here. 2,500, 2,500. Okay. Did that reduce to 6/5? Here. 3,000 over 2,500. Yeah, like 1.2. Right. Another way to say that is the price of television has increased by 20%. So 1.2, right, with the continuous model, it's e to the 0.04t. And with the annual model, it's 1.2 equals 1.04 to the power t. Okay. What's the next step?
Turn it to natural log.
Yes, introduce a logarithm. Yeah, and I like natural log. We could use natural log on both of these. Okay. And so logarithm, because what we're trying to solve for, the amount of time elapsed, is in the exponent, and the way to get it out of the exponent is to apply a logarithm. Now let's do log both sides. I'll take the natural log of both sides, and I'll do that for both of these. Natural log, natural log, natural log, natural log. Okay. And remember your log rules. Right. After you take the natural log, you can take this power and just bring it down in front.
Could you convert both into a log? Because
Yeah, you could use a common log also. I especially like the natural log on the base e because guys, what is natural log of e?
1.
1. Yeah, so that will definitely simplify this one. Right, and this one I'll just stick to natural log because why not? Okay. And so I have here natural log of 1.2 equals 0.04t, and that's it because it's times 1. Say times 1, but whatever. And over here, natural log of 1.2 equals t times natural log of 1.04. Like that?
Wait, Mr. Gifford.
Yeah.
So the natural log cancels out the e.
Yeah, natural log of e is equal to 1.
Oh yeah.
Here, try to calculate you. Natural log of e to the 1, that's natural log of e right there. Yeah, it gives me 1. It's just 1. Okay. All right. Okay. You guys good so far? All right, so what's the last step? Yeah, divide down this coefficient right here. Right. So on the continuous model, I'm dividing by 0.04, divided by 0.04. Okay. And on the annual model, I'm going to divide by natural log of 1.04. Natural log 1.04. Right. Let's see how these times compare. Again, I think they'll be fairly similar to each other, but maybe slightly different answers. So it's natural log 1, 2 divided by 0.04. I'm looking at 4.56 years with the continuous model, or natural log 1.04, 4.65 years with the annual model. Yeah, so about 4.5 years either way, 4.6 years either way, right? Not that different. Okay. All right, you guys got that? All right, any questions? All right, so we got a couple interpretations on part A, right, and we carried this over to part B and solved that. Question C. Jason decides to wait to buy a television and saves his money. Right? He puts $2,200 into a savings account with 4.7 annual interest compounded continuously. Ooh, it's really nice they specified that because now we definitely know which model to use. Determine when the amount in his savings will exceed the cost of a new television. Right, so here, I'm just going to pick one of these models and run with it. Okay. I'm going to pick the, whoops, did I misspell that? Pen US. All right, sorry, there you go, misspelled that word, continuous. Actually, you guys tell me, which one do you want to carry forward with, the continuous model or the annual model? Continuous? Okay, let's just stick with this. Right, so we're just going to pick one of these and run with it. Let's do that one. Right, so that's true. Okay. So on one hand, he's saving money and it's accumulating interest, right? On the other hand, the price of the television is going up. Oh no. So when will one match the other, right? Right. So let's put his savings on one side and the price of the TV on the other side, and we'll set those equal to each other, right? And then you'll figure out when you can buy the television. Right? Right. So the model we're using is A equals A naught times e to the RT, some version of that for both of these we're gonna do, right? So saving starts off with 2,500. Sorry, no, sorry, back up. Sorry, $2,200. Start over. He starts with $2,200. Not enough to buy the television yet, but it's earning interest at says 4.7%. So as a decimal, it's 0.047 for some amount of time, accumulating interest. At some point, that's going to match the price of the television. Then you can walk into the store and buy the television. Television starts off right now at $2,500. And then, let's stick to a continuous growth model. E to the 0.04 and t. Right. Okay. Right. Is that all right? Why I set it up that way? Okay. I think there's two large parts to this part C. Right. One is, can you set up this equation? Right? Like if I didn't do this for you guys, if this wasn't notes, would you be able to figure out to set up like that? And based on what we've done for the past couple of weeks, probably a lot of you guys could. Right? And the second part is, can you do the algebra and go solve for t? Right? Is there any questions so far? Right. Okay. So it looks like he's earning interest faster than the price of the TV is going up. Right, 4.7 compared to 4%. All right. So at some point, I'm going to have to apply a logarithm. Here, I may as well just do that now. Let's take natural log of both sides. Natural log of this side. Natural log of this side. Natural log, natural log. Okay. Now I do have two things multiplied inside each of the two logarithms. So if you guys remember back to log rules, if you have log of a times b, that's log a plus log b. You guys remember that? Okay. So maybe I have to consider that. So I have natural log of 2,200 plus natural log of e to the 0.047t. Okay. And that's equal to natural log of 2,500 plus natural log of e to the 0.04t.
And you just skip that step and just remove or put the exponent?
Yeah, that's the next step. Yeah. So natural log of 2,200 plus 0.047t is equal to natural log of 2,500 plus 0.04t. Okay, like that. Okay. Well, these natural logs now are just like some number. You can probably get a decimal approximation. I get those on one side. I'll get the t's on the other side. So let's subtract off 0.04t from both sides. 0.04t. Okay. And I'll also subtract off natural log of 2,200 from both sides. Okay, like that. All right, and that's going to give me 0.007t is equal to natural log of 2,500 minus natural log of 2,200. Like that.
Well, that's the natural log of 25 over 22.
Yeah, you could also do that. Yeah, natural log of 25 over 22. Yeah, you can totally do that. Yeah, same thing. Okay, and the last step is divide down those 0.07 from 0.007. So time is equal to natural log 25 over 22 over 0.007. All right, let's see what that is. Natural log over 0.007. All right, I'm looking at 18.3 years. Yeah, all right, it takes 18 years. Let's see if I feel like throwing that in Desmos and seeing, checking here. All right, whoops. Here, graphic calculator. All right, so let's say y equals 2,200 times e to the 0.047t versus y equals 2,400, or sorry, 2,500 times e to the power of 0.04t. Right, like that. Okay. And then here, the y-axis goes up into the thousands. So let's change this to about
3,000 and see where that lands us. Okay, like right there. All right. So the red curve is his savings. The blue curve is the price of the television. And when those two curves cross, that should be represent both the time you can buy the television and the price of the television at that time. Okay. What did we get? We got like 18 point something years. Let's see if this crosses at about 18. It is. That's it. That's exactly what we just got. Yeah, you guys got it? Same thing? Okay. All right. Any questions on that one? All right. So we got that. Let's get down to number 4, carbon dating. Carbon dating. All right, so carbon 14 has this K value. Actually, I do want to derive that with you guys and show you where that comes from. Use this information to determine age of a fossil that's well, 95% of its carbon 14 or something like that. Okay. So we got 2. All right. So carbon dating. So let's do the amount is equal to the initial amount times e to the kt, right? And for exponential decay, it's common to throw in a negative and into the exponent so that k comes out to a positive value. Yeah, a0, the initial amount. Yeah. Right. So guys, all I did is I just wrote this right here, this right here. So a naught's the initial amount, a is the final amount or the amount at some time in the future. Okay. All right. So guys, 1/2 life. That means that in the case of carbon 14, if T 1/2 is 5,730 years for carbon 14, okay, that means if I plug in exactly that amount of time for T, then what is the A compared to the A naught? It's always what? Half. Yeah, because it's decayed to half. So I'll end up with half of what I started with compared to what I started with. If I plug in 5,730 years for T. Sure. All right. Do you guys see that we can solve for K? Now, your textbook told you what K is, but I want you guys to see where it comes from. Okay. Wait, you guys good? Okay. All right. What can I do next? The initial amount doesn't actually matter. What matters is the half-life and the proportion. Right? Okay. What's the next step? Take the I have to apply a what? Starts with an L.
Logarithm.
Logarithm. Let's do natural log of 1/2 equals natural log of e to the negative 5730k. Still solving for k. Okay. Oh, well, what is all this on the right side? It's just negative 5730k. K right there. Okay. So we're solving for k. And that's equal to hey guys, natural log of 1/2. Let me show you guys something cool. Natural log 0.5. Okay. Here's a decimal approximation, negative 0.693 something. Can anybody think of a different way to write that?
Natural log 1 minus the delta.
Yes. Natural log 1 minus natural log 2. And what is natural log of 1?
0.
0? So 0 minus natural log 2. Isn't that just negative natural log 2? So is that really the same thing? Negative natural log 2. Negative 0.693. Hey, that's the same thing. Same thing. It's kind of interesting. Make these connections. But we're one step away from getting k, which is divided by negative 5730. Negative 5730. Okay. So let's do that. And it's going to give us a k value of, it looks like the negative is going to cancel. So it's natural log 2 divided by 5730. Okay. Do you guys see in general, I mean, if you pause for a moment and step up, big picture, if you know the half-life of something, for carbon 14, it's 5730 years. If you very simply take natural log of 2 and divide by the half-life, that will tell you the k value. You see it? Okay. So 0.000121 it rounds to. I like that. And the unit is 1 over years. Okay. Now your book said k is 0.00012. There you go. All right. So now, what if there's a fossil that has lost 95% of its carbon 14? Guys, if it's lost 95% of its carbon 14, okay. So it starts off with this much carbon 14. There's like the initial amount. Here's how much it has. Guys, what is this compared to this? 5%. Yeah, isn't this 5% of the original? All right, so that's what we're working with. So the amount is equal to the initial amount times e to the 0.000121 times however much time has passed, which is what we're solving for. Right? And this is 0.05 times a naught. And they never told us what a naught was specifically. Right? It's like some concentration, and like right now, all of us have a tiny proportion of carbon 14 inside our living cells. Right? This kind of dissipates as soon as we die. Right? So it's like really some concentration. Right? But the initial amount doesn't matter anyway. It's really proportions that matter. All right, so natural log, both sides. Let's go ahead and skip to the next step because you guys just saw that. I can just do that, right? Natural log, and then on the right side, the ln and the e cancel.
Wait, so is K always 0.00121?
Guys, is K always 0.00121? It is for carbon 14. Yeah. Right. Now, if you switch to a different radioactive isotope like thorium 230, then that would be different. Yeah. But for carbon 14, it's always that number. Yeah. So what is natural log 0.05? Oh, one more detail. Guys, I missed one little detail. I just noticed it. Okay. Does anybody see?
Negative.
Negative. Yes. Guys, this should be negative, negative. This is negative. And then negative, negative. Right. Because I know if I take natural log of anything between 0 and 1, it'll be negative. So, oops. Right. So now we're back on track. Right. Divide by negative 0.00121. Right. I'm looking at the amount of time that's passed is 24,000 years. Right. So this artifact, that'll, now I think that makes sense because, like here, let's do big picture approximation. You guys see the half-life is between 5,000 and 6,000 years. You guys see that, right? Yep. Now, according to the answer we got, 5 to 6,000 would basically be about 4 half-lives, maybe something like that. What is 24,760 compared to 5,730? Right. It's like 4 point something half-lives. Right? Well, if you start with 100% of something and you multiply it by half, you do that 4 point something times, it gets you down to only 5% of what you started with, which is what they told us at the beginning. Right, how about part B on this? It says, what about an animal skeleton that has 95% of its carbon 14 remaining? Carbon 14. Okay. So we'll do A equals A naught e to the kt. Okay. But now this is 0.95 of A naught equals A naught e to the negative 0.000121 and then t.
Wouldn't it be negative K at top?
Oh yeah, let's do it. Yeah, good call. Yeah. All right.
Is this the same equation?
Yeah, the only difference is now we have 95%. Yeah. So like that. Right. Guys, if you have 95% of what you started with, I think barely any time has passed at all. Right? Like maybe a few hundred years, maybe something like that. But let's find out. So natural log of 0.95. Because guys, if this was 50%, guys, if you're down to 50%, you know exactly when half-life has passed, which would correspond to 5,700 something years. Okay. We're at 95%. Yeah. So not a lot. So negative 0.000121 t. Okay. Divide both sides. Negative 0.000121.
Yeah, so. You can tell he is our two.
Yeah, that looks about right. 420 something years old. Yeah. All right, so maybe that artifacts from like 1600 or something. Ooh, about Shakespeare time. How about that? All right, you guys got that? Um, okay, so let's see. We did an exponential growth. We did an exponential decay. Okay, here, I had some of these other ones queued up, but I do want to give you guys some time to also work on Alex. So here, I'm just going to point out some of these two guys. Okay, so nuclear power, we got plutonium 239 is radioactive. Well, we just did a radioactive decay. So you guys could, and that saw this one based on what we just did. Modern whales appeared so many million years ago. Oh, we've got another carbon dating for number 10. Was going to do, yeah, but we just did carbon 14 dating, so it's really kind of the same thing, what we just did. This one looks like it would have been fun. Is the population of our town grows exponentially? It's currently 68,000. 1 year ago, it was 67,000. Okay. Could you create an exponential curve out of that, and then go back in time about 100 years ago and estimate the town 100 years ago? Right, to do that too. All right, but again, if you guys want to see lots and lots of other examples, I did upload like all these ones that are green highlighted. This one wildlife, this one depreciation, right? This one population, this one half-life, right? Plus all the book examples at the beginning. Right? Those are all in the longer video, so you can see lots and lots of other examples. But it's nothing different than the notes that we've done in class today. Right, so double check, make sure your name is on your notes. Turn in your notes. I'll give you guys points for those. And then you guys got the rest of the class to start solving those on Alex or ask me any questions or see any other examples you need.